All right, let's see if we can use some of that work and energy, elastic energy type stuff we've been looking at a little bit in a situation. So here we've got a dog, 14-kilogram dog attached to like a little harness with like a rope or a leash or something like that attached to a little post. And the leash has got a spring constant of 780 newtons per meter, and he's stretching it 24 centimeters. So we're going to find a couple things, but first of all, let's find out how hard is the dog pulling on the leash. And there's a couple ways we can actually do this, and it doesn't really matter which way we do it, but we'll try it a couple different ways and we'll see how things go. So one thing that you could do, it's really, really simple, is you could just go back to the basic expression from the linear function, f equals kx, and we could do it that way. So we have the k value, that's the 780, we've got the x, that's the 24, and if we multiply the two together, we can find out the force he's pulling with. So just multiplying the two numbers together, we got about 187 newtons. So that is how hard the dog is pulling. Now, another way you could have done the question, you'll end up with the same answer. Another way you can do it is some people would look at in terms of doing F equals kx, they would look at the energy stored in the actual leash. So if we go to the energy expression, that was 1/2 kx squared, we can solve for that as well. We've got the 1/2, we've got the k, which is the 780, x squared, which is this. And if we do that, that would be equal to about 22.5 joules. So there's about 22.5 joules of energy stored inside of the elastic. So this is how much work the dog has actually done in order to actually stretch out the leash. Now, what some people do is then they would then take that and make that equal to work, which is then force times distance, and calculate the force that way. So if you take that expression, do the 22.5 and divide it by the distance, which is also going to be the x value because that's how far it's been stretched. If we divide those two out, we got the 22.5 and we divide that by the 0.24, we will get about, rounded off, we got about 94 newtons, which does not match up to the other answer. But notice that this one is about half as big as this one. Well, that's because work equals FD, that force either has to be constant or in this case, average. So this was the average force that we found. So since it's the average force, it started at 0 newtons and goes up to something, and this is the average, we would actually have to double it, and then once we double it, we'll get pretty much the exact same thing as the other expression. So that's two ways you can do the exact same question. It doesn't really make any difference how you do it. Some people like to look at the energy, some people just jump to the F equals kx. It doesn't really make any difference. The only thing you got to be careful of, especially with springs and elastics, if you do that work equals FD, you got to ask yourself, is that constant? Well, if it's not constant, then you got to use the average. And luckily, springs and elastics, for what we do, change a nice linear rate. So it's really, really easy to incorporate that. So now let's expand on the situation a little bit. The dog is actually, of course, pulling on the leash towards the right, and the leash is pulling back to the left. And he's not going anywhere, and he's trying to get to his bone over there. Well, what's keeping him in place, the leash is trying to pull him back, but of course friction is actually holding him in place. So let's see if we can find the coefficient of friction between the dog and the ground. Well, it's not that hard to do. He's in static equilibrium. He's not going anywhere. So we can sort of try and piece things together. So if we know how hard he's pulling, well, we do know how hard he's pulling. He's pulling with 187 newtons. Well, if he's pulling with 187 to the right, the leash must be pulling with 187 to the left, so everything cancels out, and keeping him in place would be friction, and friction's got to be the 187, because he's pushing with the 187 back in the ground, that keeps him in place. So the friction has to be 187 newtons to keep him exactly where he is. Everything's canceling out. So in the coefficient of friction would of course be FF over Fn, and in this case Fn would just be the mg. So 114 times 9.81, so that's really, really simple. And then we can divide this 2 out. We've got the friction's got to be 187 because that's how hard he's pulling. He's not going anywhere. We can divide that by his weight, which is going to be around 130 or so. And we've got a coefficient of friction of 1.36, give or take a little bit. Okay, so the thing about this one is you got to be careful which force you're using, especially if you used this kind of solution. Don't use the 94 because that was the average force. You'd want to use the force he's actually pulling with at the very, very end. So make sure you use the 187 and not the 94. Okay, so let's look at a slightly different situation. Get rid of this. Delete. All right, so let's look at a different situation. Okay, so here we have a little elastic situation, Spider-Man hanging on his web, and let's say he's 86 kilograms, and he's going to stretch the web 62 centimeters, and we are going to try and find out what is the K value for his web. Now, the first thing I'm going to do is I'm going to show you the wrong way to do it. So if when people see like this stuff like this, things going vertical and stuff, and gravity stretching things out, a lot of people, what they'll think about is gravitational potential energy of mgh. And what they'll then do is they will then take that, gravitational potential energy that has changed and that has gone into the web as elastic energy and make them equal. Now, if we do that, we can do it. It's not that hard. I'm going to show you, and this is not the right way to do it, but we'll just adjust things a little bit later on. So if I calculate the mgh, I know his mass. That's easy. I got the 86. I got the 9.81 for gravity, and I've got the 0.62 meters. That is going to be equal to 523 joules of gravitational potential energy. And then people often they'll do is they'll take that and they'll put it into the 1/2 kx squared expression. We have the x value, that would be the 62, and we can solve for the k value for the spring. So we take the amount of energy times by 2, we divide it by the 0.62, do not forget to square it, and we can get a k value for the web of around, let's say 2720 newtons per meter. Now this is not right. Now the reason why this is not right is this part right here. That is the force of gravity, and the force of gravity, the full force of gravity, is not acting on Spider-Man during the entire stretch. The only time Spider-Man's full weight or full force of gravity is actually applying to the web is at the very, 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 very end. At the very beginning, he's applying 0 newtons, and then there's more and more and more, and at the bottom, that is when he's actually pulling with his full mg. So you can't just do mgh. It doesn't quite work this way. If you remember from our previous stuff, that force, doing force times distance, which is basically what this is, this has to be the average force that was actually used. So we need to take that 523 and cut in half, because we need to use half of this force, not the entire thing. So if we would cut this in half, it would cut this in half, which is then going to make the k value about half as big. So if we do that, take this, we cut that in half, now you're looking at more of a correct k value for the elastic, which would be around 1360 newtons per meter. Okay, so this we got to be careful when you're hanging things on springs and stuff like that, or elastic things or elastic bands. Be very careful using the force of gravity, because you typically want to cut it in half and use the average force if you're just going to do like a basic FD type thing. So let's look at a slightly different way to do it. Another way people would do it is not to use that expression. What people would do instead is just do the F equals kx expression, which is a little bit easier, because when you use this one, this isn't work equals force times distance. This is the maximum force that's actually being used. So of course that would be at the very, very end. So that would be his mg. So just doing mg is equal to kx, this is a little bit of an easier way to do it, and you don't have to worry about messing up that force over there. So if we do that, we can calculate our k value. It would be mg divided by x. Okay, so we've got that 86. We'll times that by the 9.81 to get our force of gravity. We divide that by the 0.62, and we get around 1360 newtons per meter, which is exactly what we have over there. So some people like to do it this way. That's fine. There's nothing wrong with that. Just make sure that you use the average force here, so it doesn't end up being twice as big as it's supposed to be. And some people will just use this method. It doesn't really matter which way you do it. Either way will work just fine.